Method of sections. This is 6.4. Well, in earlier chapters we assumed bodies to be rigid. We modeled the entire object or machine as one piece in equilibrium, and then we used the free body diagram, weight, forces, etc., and found reactions at the supports. And then in chapter 6, beginning of chapter 6, we used the method of joints to model the body as non-rigid. In other words, we looked inside the body to try to find the force inside one or more of the members by breaking it into pieces and then analyzing each piece as a rigid body or each joint as a rigid body using method of equilibrium. So now we can take that non-rigid body and treat sections of it as rigid using the method of sections. We'll use equations of equilibrium to analyze each section. So basically what we have done here in chapter 6 is we took a non-rigid body like this and took a section of it, analyzed a section. Now actually we've been using this concept for several chapters already. Anytime you separate your system from its surroundings and then define your system as a subset of the whole system, we're using the same concept. In chapter 3 we took this system, we took a subset of the system and treated it as a rigid structure. In other words, we said it's not moving, it's in equilibrium, all of the forces have to be equal to 0. In chapter 5 we took this rigid structure and we broke it apart, and we took only a portion of it and treated it as rigid by drawing the reactions, and we had this two-force member on here. That's a portion of the rigid body that we treated separately. The same thing with this. We took the portion of the rigid body and treated it separately. It was a two-force member in compression, and anytime we take that portion and treat it as a rigid body using the equations of equilibrium that apply, that's the method of sections. In chapter 6, again, we did this same sort of thing. All right, so here's our steps. We're going to take the entire body, we're going to analyze the reactions, keep it together, basically treat it as rigid, and then we're going to find a good section that applies to minimize some unknowns. And in trusses we're only going to cut no more than 3 members. We'll draw a free body diagram of the section, and then we're going to use the equations of equilibrium. Now we will generally use a moment equation that can have a reference point that could be either on or off of our section or of the rigid body. We're going to guess at the positive directions of the two-force members, and generally it's easier to draw them in tension unless we know different. So that's what I'm going to do here as a model. All right, so let's say we have this truss structure and we only want to find a piece of them or a portion of them. Let's say here we want to find CD, CF, and GF. Well, here's CD, here's CF, and here's GF. What we can do is take a little section. I'm going to just draw it as a squiggly line and then take this half and separate it from that half. And that's what I've done here. So I'm going to take CD, I'm going to draw it as a tension member on both sides. I'm going to take GF and draw it as a tension member on both sides. And I take CF and draw it as a tension member on both sides. Now what I've got is 2 separate rigid bodies. This can be analyzed to solve for the equations of equilibrium, and then you can find out those 3 unknowns. Or we can take this side and solve for those 3 unknowns by treating it as a rigid body in equilibrium. All right, so the first thing we want to do is find the reaction. So I'm going to do that right here. I'm going to take it, before I cut it apart, I'm going to use this and find the reaction at E. So let's do that. Sum of the moments about A equals 0. So here I have -6 times 3, -8 times 6, plus EY times 9 equals 0. Solve that for EY is equal to 7.33 kilonewtons. I guess I should draw the forces on my free body diagram. I forgot to do that. EY, AY, and AX. Again, we know that A has an AX because it has the pin. EY does not have a pin, it has a roller, so therefore there is no EX associated with that. All right, let's label the forces on our free body diagram then. Or our section. I am going to use this section. You could use this one and solve for those three unknowns, or you can use this one. You can use them both. I'll try to, in this case, I'm just going to use the left one. So I'm going to call this CD. And this one will be FC. Let's call it DC because it's heading away from point D. And I'll call this FC and this one FG. Okay. Now we can, again, do more than one approach here, but I am going to sum the moments about point F and see if I can solve for DC. The reason point F is a good choice is because FG goes through F, the 8 goes through F, FC goes through F. The only force I have left is EY. So let's sum moments about F. Put a smaller pen, equals 0. So here I have positive DC times the height here. Ooh, I didn't actually figure out that height. Maybe I should do that. That height there is 3. This is, because this is an equilateral triangle, each one of those angles is 3. So this would be 3 sine, oops, that's kind of bad, 3 sine 60. So then our lever arm here is 3 sine 60 for DC. So I'll put that, 3 sine 60 plus EY times 3 equals 0. And I can solve that for DC is equal to negative 8.46. So anytime you draw something as a tension member, you get a negative value. That means it's actually in compression. So I'm going to say that that's equal to DC is 8.46 in compression. And that's how I want you to express things. Is I should probably put the units there. Let's start over again. 8.46 kilonewtons in compression. Well, let's see if we can solve for the rest of these forces. Let's sum the forces in the y and see what we get. In the y direction, I have this EY, this 8, and this piece of FC, which would be the sine component of FC. So let's go ahead and put those in. So sum of the forces in the y is equal to 0. So EY is positive minus 8 plus FC sine of 60 equals 0. I can solve that for FC, and that's going to be equal to 0.77. Let me go ahead and put it down here. FC is equal to 0.77 kilonewtons. I got a positive value. I drew it as a tension member, so I keep it as a tension member. I have that one as tension. All right, let's find this last piece, which is FG. I have 3 forces in the x direction. This one, and this one, or this component of FC. Clearly, though, I've got them all pointing to the left, and that doesn't make sense. So one of those or more of those is going to end up being negative. So let's go ahead and put those in here and see what we get. Sum of the forces in the x is equal to 0. So I have minus FG minus FC cos 60 minus DC equals 0. Now this is the one I'm looking for, is FG. FC is a positive tension. In my picture, I've drawn it as a negative, as positive, so I'll keep that one there. DC, I have solved this as a compression member, so it is actually going this way. So when I put it into the equation, I have to, basically, if I've drawn it in positive here, but I have a negative number, then I have to change the sign when I put it into the equation. So that's just a little bit tricky. on how you make sure you do that. So FC is 0.77, and this would be cos 60, and then DC is 8 plus 8.46, and that's equal to 0. Solving that for FG, I got that as 8.08, and that is tension. I drew it as a tension member. I solved it as a positive number, and so we'll keep it like that. Okay, let's look at this truss here. 634. What we're looking for is KJ, CJ, and CD. Now we only want to cut 3 members, no more than 3, or we have too many unknowns. So it makes pretty good sense that this would be the place to cut it. So we're going to separate the left side from the right side. When we do that, I guess first I shouldn't forget, we should first do the reaction. So let me go ahead and put the reactions on here. I have AY, AX, and GY. Again, we know that G is only has Y force because that's a roller. This is the pin, so we know that that has both X and Y. Some of the moments about A we can solve for GY, AY, and AX. Now let's take those two sections. Let's draw the forces on our picture. Again, I'm going to draw them all as positive, so KJ, and then I'm going to draw that as positive on this one, KJ. Now again, we can either call it KJ or we can call it JK. It's going to be the same thing. I'm not sure if there's a real requirement there, but we'll call that CD, and this one is DC. I kind of like to draw them the from to, putting the letters from the point to the next point, but this one would be CJ, and this one would be JC. Okay. We can solve either side. It doesn't really matter how we do it. We can do this one or we can do this one. We've already solved for the reactions. So let's look at the left side first. So here's the solution for the left side. Oh, I forgot to transfer these forces. So let me just say this is KJ, CJ, and CD. All I have to do is sum the moments about some point, or do the forces about some point. Looks like I missed this, so let me say this is the sum of the moments about C equals 0. Looks like I cut my answers off there. If I sum the moments about C, CJ goes through C, CD goes through C, 5 goes through C. So I have AY, should draw that over there, AY. AY has this lever arm going in this direction. KJ has this lever arm going in this direction. 4 has this lever arm going in this direction. And then I can solve that for KJ. That's equal to negative 11.11, which means that's in compression. I did draw my arrow incorrectly there. To find out the rest of the pieces here, I can sum the forces in the Y. And then this has an angle associated with it. Didn't solve for that angle in this picture, but I should have done that. That's angle theta, and it was 56.31 degrees. You can go back and solve for that. You can find that CJ is a negative when I drew it like that, which means I drew its arrow incorrectly as well. It's actually a compression member. Sum of the forces in the X is equal to 0. So in this case I have this one, which is actually negative. That's what there is. That's KJ. So let me go back to the equation. When I put them in the equation, I should put them all that agrees with the arrows. So KJ, CJ sign, and CD. When I put the values in, then you have to keep track of whether or not it's a negative as you previously solved for it. And so I got that one as negative, CJ was negative, and CD is a positive, and I can solve for that. Now what I said is that you can sum the moments about any point, either on or off the body. So I'm going to use just a little bit different technique here to try to solve it using the right side of our section. Again, you can use either side. It doesn't really matter. So let's do this. I want to solve for all of these unknowns in the same way. I have gy, should put that in here, gy, and that is equal to, how much was that? 12.67. Then I have these other applied forces. What I can do is, again, sum the moments about any place on or off the body. So I'm going to pretend that point C here is, well, again, I'm not going to pretend it's on the body. I'm just going to sum the moments about point C and see what I can do. All right, if I do that, JC goes through C, DC goes through C, JK has this lever arm, 8 has this lever arm, 2 has this big lever arm, GY has this big lever arm, and all we have to do is just sum the moments. So I'm going to sum the moments about C equals 0. So I have JK times my lever arm of 3. This is a height of 3. It doesn't show up on this picture. Minus 8 times 6. I beg your pardon, that's 4. Minus 6 times 6 plus GY times 8 equals 0. Now I can solve that for JK, and that's going to be equal to negative 11.11, which basically means that I drew the arrow incorrectly. So JK is equal to 11.11 kilonewtons in compression. And fortunately, that's the same answer that I got with my prior work. I can also solve now for the other two. Let's sum the forces in the y. I have minus 8 minus 6 plus gy of 12.67. Yeah, it's kind of sloppy here. 12.67. Now the other force I have is JC, so that would be minus JC sine of theta. And we had theta on the other picture of 56.31 degrees, so I'll just go ahead and put there 56.3 degrees. That's equal to 0, and I can solve that for JC is equal to negative 1.60, which means that it is equal to 1.60 kilonewtons in compression. That's equal to JC. Again, that agrees with my work from the other side. And we can sum the forces in the x is equal to 0 to solve for my last unknown. There's only 3, but I draw them all in here. So here I have minus DC minus JK minus JC cos of the angle 56.3 degrees is equal to 0. Solve that for CD, or DC, is equal to 12.0 kilonewtons in tension. Okay, there we go. We got the same answer both ways, and so that's handy. Well, lastly, I just want to point out a couple of the homework problems I want you to work on. This is a textbook picture. I'm asking you to solve for something just slightly different here. But in this picture, if you want to find member BC, which is right here, there are really two ways to cut it. You can cut it this way, or you can cut it this way. Either way works. I don't think one of them is more difficult than the other. But again, you can't pick more than 3. You shouldn't cut more than 3 members. So you can either cut it vertically or horizontally. All right, using the method of sections, determine the force in HG, GF. How do we do that? We might also ask for BC. I think the problem asks for BC as well. But let's look at HG real quickly. HG over here. How would I get that? I could probably cut this way, and you could solve for then drawing BC and these guys going that way. Another way to look at it is looking for some obvious things. If you know that this over here is a zero force member, you can observation know that this one is a zero force member. You know that these are collinear pairs, and if that's the case, this one is equal to that one. So in this case, you can actually go faster by recognizing, again, this one is 0, that one is 0, this one is 1.5, and you could make a cut over here, go faster, find that one first, and then just say, by observation, I know that FG is equal to HG. You can get them both by doing that. You may still have to do some work to find out BC, but I'm just giving you a hint that there's sometimes more ways that you can approach these problems if you look for the obvious zero force members and collinear members.